All right, so this is the second part of the kinetics lecture. We'll begin on slide 41. So now we have moved over to second order reactions. So the curve of a second order reaction on the left looks very similar to a first order reaction curve. Hard to tell the difference between the two just looking at them. The way to tell the difference is to plot the graph of 1 over the concentration versus time. And if the plot produces a straight line on the right which has a positive slope, then the reaction is second order. So you should become familiar with these two sets of graphs, for the first order and for the second order. It could be a simple AP multiple choice question that would ask you to identify what type of reaction it is by showing you the graph on the right. And the thing you want to notice is what is on the vertical axis. Is it natural log of the concentration A, or is it 1 over the concentration A, and what is the slope of the graph? So, make a mental note of that. All right, so the equation to create a linear equation from a second order reaction is, again, it's a y equals mx plus b format line, and it's 1 over the concentration, no natural logs here, equals positive k in this case times time plus 1 over the initial concentration of A. The equation for the half-life of a second order equation, remember we said when we talked about the half-life of a first order equation that it always was going to have the same time interval for every half-life. That's not true of a second order equation. And so it's actually one that you would have to calculate using the concentration. So it depends on the concentration. For the first order equation, it did not depend on the concentration. It was always half of what the preceding concentration was. But now the concentration is going to change what the half-life is. Okay, so it's half-life is 1 over the rate constant times the initial concentration of the reaction. The half-life of a second order reaction depends on the beginning concentration A0. As the concentration A0 gets smaller, the half-life gets longer. So it takes more time to use up the reactant. So in this case, the half-life is wherever the reaction is at a particular moment in time. And we'll do some problems and you'll see some examples of this. All right, now for a zeroth order reaction, and the equation for the half-life of a zeroth order reaction is, well, the rate law first of all is rate equals K times concentration to the 0 power. That's the definition of a zeroth order reaction. So that simply equals K. So rate equals the rate constant means that the concentration of the reactant does not affect the reaction. Rate equals K means concentration is irrelevant. It has no part in the equation. So the concentration will decrease at a constant rate in a straight line. So initially it looks kind of like the decrease for a first order reaction. But again, look at the vertical axis, the axis on the left side. It is just A, just simply the concentration of A versus time. So let's review those. For a first order reaction, the vertical axis is going to be natural log of the concentration of A. For second order, it's going to be 1 over the concentration of A. And for a zeroth order, it's going to be just the concentration of A directly. The order of a reaction can be determined by creating a table such as the one shown above and graphing the time versus each of the functions that creates a straight line for 0th, first, and second order. And the order can be determined by if time versus concentration of A is a straight line positive slope, then the reaction is 0th order. If time versus the natural log of A is a straight line with a negative slope, then the reaction is first order. And if time versus 1 over the concentration of A is a straight line with a positive slope, then the reaction is second order. If none of these produces a straight line, then the reaction is some other order other than one of these three. Okay, so here's a sample problem. The decomposition of a gas A is monitored as a function of time at a certain temperature. If the plot of 1 over the concentration of A versus time produced a linear straight line plot with an equation of y equals 0.0296x plus 200, what is the order of the reaction? So the answer to that is, since the plot of 1 over the concentration of A versus time produces a straight line, and it is a positively sloping straight line, then the equation above is the equation for the straight. The equation above is the equation of a straight line with a positive slope. Then the reaction is second order. So the second question is, what is the rate constant? Well, the rate constant, just as it was in the last example, is going to be the number in front of the x. So the rate constant is the slope of the line, which is 0.296. Beginning with a 0.1 molar concentration of A, what percent of A will react after 5 seconds? So again, you want to identify the different variables. So you want to enter 1 over concentration of A, 1 over initial concentration of A, and T into the equation. So we have the equation there off to the left, and T is 5 seconds. Then you go ahead and substitute in your numbers. Again, the rate constant K is 0.296. The initial concentration is whatever the problem gives you. It's not the 200. The 200 is just simply an initial for that line. But you go ahead and you place the initial concentration that specific question is asking for, not the generic number that's there, which is a 200. You go ahead and just plug in the numbers and run them on the calculator, and you get 1 over the concentration of A equals 101.48. You then take the reciprocal of that and you get 0.0985 molar. So this is the concentration of the reactant remaining after 5 seconds. This means that 0.1 molar, the original concentration, minus 0.0985 will give you 0.001 molar was used in 5 seconds. The percentage reacted, what is the percentage reacted? So this is slightly different than the last question, is simply what you used up, 0.001, divided by what you started with, 0.1, and then you multiply by 100, and that gives you 1%. So 1% of the reactant was used in the first 5 seconds. All right, now we're going to move on to a topic called collision theory, and you should be familiar with this. It's more of a concept than a conceptual idea than anything that you have to do any calculations with. So collision theory states that the rate of a reaction will increase with 1, increasing the number of collisions of reactant molecules, and 2, increasing the speed of the reactant molecules. So a collision must collide with enough energy to create a reaction. The energy required to cause a chemical reaction. The energy needed for the reaction to proceed is called activation energy and is the highest point on the diagram. So you should be familiar with that. That's the energy diagram for a reaction. So let's go over what that's saying. If you start with reactants A and B, you need to get up over that hill in order to get the reaction to take place to produce the products C and D on the other side of the hill, over on the right side of each of those graphs. If you get up to that highest point, it's possible that the reaction could go backwards to A and B again. In other words, it won't go over the hill, or it could go over the hill to C and D. The difference between the initial energy where the reactants are, A and B, and that highest point is called the activation energy. Now in the first graph, the one on the left, you'll notice that it goes down a hill and ends up lower than it was at the beginning. C and D are below A and B. That's an example of an exothermic reaction because it means the reaction ended up at a lower energy state than it started, and therefore it must have released energy in order to get to that lower energy state. On the right, the graph shows A and B. It has to go up to get over that hill, and then it comes down to C and D, but it ends up at a energy level for C and D that's higher than A and B. That's an endothermic reaction. That means the difference between where C and D is and where A and B is the amount of heat that had to go into the reaction, and that would be an endothermic reaction. In both cases, though, remember this, that in both cases of an exothermic and endothermic reaction, you must first put energy in to get the reaction started. What determines exo or endothermic is where it ends up after it goes over that hill. Does it end up lower than A and B, or does it end up higher than A and B? So this reaction is exothermic. Again, another example of this, because the reaction ends at a lower energy than it began, so energy leaves the reaction. That would be a negative delta H, negative change in enthalpy. On the right-hand side, this reaction is endothermic because the reaction ends up at a higher energy than it began, so energy enters the reaction. That's a positive delta H, positive change in enthalpy. Activation energy is the minimum energy required to allow A and B to break apart. Once A and B have broken, they can go back to A and B, or they can recombine to become products, C and D. For both endothermic and exothermic reactions, energy must first be put into the reaction and must reach the activation energy. The broken molecules that exist at the top of the diagram are called the activation complex. Okay, as temperature increases, the rate constant K increases. The higher the temperature, the greater the rate constant increases. So we've talked about this earlier, that the rate constant is really dependent on one thing, and that's the temperature. We haven't talked about how they're related. So as we see from this graph, it's just a conceptual graph. It doesn't have any numbers. But we see as you increase the temperature on the horizontal axis going from left to right, the rate constant will go up. But what you'll notice, as the temperature gets higher, the rate constant goes up at a faster rate. It goes up faster than it does earlier on. So as temperature gets higher, the rate constant gets higher at a faster rate than it was at lower temperatures. The curves below are called Maxwell-Boltzmann distributions, and the area under the curves is the same for all four curves. So you have a certain chemical reaction. It has a certain number of particles or molecules, or you can think of it as moles. So the number of moles or molecules is the same underneath all four of those curves. The only thing that differentiates them is the temperature. And you can see at the lower temperature you have the turquoise curve, and it's much taller and it's more to the left than the other three. The highest temperature curve, the red one, is at 1000 K, and that is flatter, and more of that curve is off to the right. What that dashed line is that's the activation energy, and we're just assuming that that's some hypothetical molecular speed of the molecules. So the area under the curves is the same for all four. The red dashed line represents the activation energy, and the minimum energy required, that's the minimum energy for the reaction to take place. So higher temperatures means higher molecular speed. So the activation energy on the graph is 1000 meters per second. So none of the molecules under the turquoise curve have enough energy to react. But roughly half of the molecules under the red curve have enough energy to react. So that's what this curve is communicating to you. Generally, there's no math that they would ever ask you to do on this other than to recognize what the curve is and to be able to interpret what it's communicating to you. Okay, the Arrhenius equation. The Arrhenius equation relates temperature, activation energy, and the rate constant. The Arrhenius equation is K equals A, E, and then E is raised to the exponent negative EA over RT. So what is A? A is called the frequency factor, and it takes into account the orientation of the molecules and a few other factors. That is nothing that you'd have to be able to derive what A is. That's something that you would be given. So orientation is important because molecules must strike each other in the proper direction. In other words, if I take a ruler and want to break it over the side of the table, if I hit the ruler on the end of the ruler, it won't break. but if I turn it sideways and hit it against, hitting it long ways against the side of the table, it will snap pretty easily. So it depends on which direction that I have the ruler oriented in order to determine whether it's going to break. EA is activation energy. That's the top of that hill that we talked about a few slides back on the energy diagram. That's the amount of energy a molecule or compound must have to react. So EA is the energy mountain that molecules must climb in order to react. T is the temperature in Kelvin. R is the gas constant. Now there are several different versions of the gas constant, and you have to be sure you use the right one for each situation. For PV equals nRT, if we were dealing in atmospheres, then we use the 0.0821 liter atmospheres per mole Kelvin. But for this particular equation, you need to use an alternate one, and that is 8.314 joules per mole Kelvin. So the joules takes the place of the liter atmospheres in the unit of measure. Anyway, if you use the wrong gas constant, you're going to be off by a factor of about 100. So you want to watch that. And then E is the same E that we've used before. That's Euler's number, 2.718. The Arrhenius equation relates temperature, activation energy, and the rate constant. Okay, so what is the relationship between that exponent, negative EA over RT, and the rate constant K? Well, if we just take a look at it conceptually without plugging in numbers right now, as the activation energy, EA, gets higher, the term negative EA over RT becomes more negative. So as the numerator of that fraction becomes larger, then that negative term becomes more and more negative. So K decreases, and that gives you a slower reaction. And think about that logically. If you increase the activation energy, it's harder for the molecules to get over that energy mountain to react, and therefore you're going to have less of a reaction. The reaction's not going to take place as quickly. So this happens because a particle requires higher energy to react. Fewer particles have this amount of energy, so the reaction slows down. At a temperature, as the temperature T gets higher, the term negative EA over RT becomes less negative. So K increases. It's a faster reaction. And this happens, just think about it conceptually, this happens because higher temperature puts more energy into the particles, so more particles reach the activation energy and speed up the reaction. And then as the term A increases, then obviously K and the rate of the reaction will increase. So A is called the frequency factor, and it takes into account, one, how frequently the molecules collide with each other. So in liquid molecules, they collide more frequently because they're closer together. As you know, liquid molecules are touching each other. Two, the orientation of the molecules. Molecules will break apart only if they collide facing in a certain direction. So the Arrhenius equation relates temperature, activation energy, and the rate constant. The Arrhenius equation can also be written, and you don't need to understand the math again. Just understand that this was derived for you. And there you see it. It's natural log of K equals negative EA, activation energy, over R, the gas constant, times 1 over the temperature, plus the natural log of the concentration A. Or excuse me, not the concentration A, take that back, of the frequency factor A. So you can see it again has the slope intercept form of a straight line, y equals mx plus b. So again, why do we use natural logs? To create a straight line of the data. So the slope of this line is negative EA over R. The independent variable is 1 over the temperature in Kelvin, and the dependent variable y is the natural log of K. So we can calculate K at a certain temperature if we know K at another temperature. So there's the equation that was shown on the previous page. So earlier we said that the rate constant K is a function of temperature. So remember, the glow sticks became brighter in warm water because the reaction was faster. At that point, you had a different value of K than when they were not in the warm water. We can apply this equation twice to the same straight line, to find different rate constants at different temperatures. Again, you don't need to understand the math of how you get here, but just understand if you took this equation up on the top for a value of temperature and a value of K, and then you wanted to figure out the value of K at a second temperature, at a different temperature, you can use the equation down below. So it's the natural log of rate constant 2 over rate constant 1 equals negative activation energy over R times the quantity 1 over the temperature of reaction 2 minus 1 over the temperature of reaction 1. So we know that K changes with temperature. This equation gives us a way to take the known rate constant K for a particular known temperature and figure out the rate constant at a different temperature. And you could also do it, mix that around. You could have two different rate constants and a temperature and figure out the second temperature. You can just figure out whichever variable is the unknown. So the activation energy for the following first order reaction is 102 kilojoules per mole. So that's the EA. And there's the reaction, again, a decomposition reaction. The value of the rate constant K is 1.35 times 10 to the minus 4, 1 over seconds. And at 35 degrees centigrade, which is 308 degrees Kelvin. What is the value of K at 0 degrees centigrade? So you know the value of K at 35 degrees centigrade. They want you to find the value of K at 0 degrees centigrade. Since it's colder, we would expect it to be lower. It looks like you're putting it into ice water there. And so that would be a lower value of K. The reaction won't happen as fast. That's what you'd expect. But let's go ahead and work the numbers on this. So there's the equation. And it really is just a case of plugging in the numbers, but you have to practice these. It's very easy to make mistakes on an equation like that if you haven't practiced. So the activation energy is measured in kilojoules per mole, but the gas constant R is measured in joules per mole Kelvin. You see that down at the bottom. So this can be converted from kilojoules to joules because the gas constant below is measured in joules. So EA, rather than saying 102 kilojoules per mole, it's 102,000 joules per mole. Again, just get used to this conversion between joules, kilojoules, grams, kilograms, liters, milliliters, things like that, that you can do them quickly in your head. So it's 102,000 joules per mole. And so the gas constant is 8.31 joules over mole Kelvin. So it's a lot of numbers here, but that's all it is a lot of numbers. There's no algebra involved here. It's really just crunching the numbers. So we plug in all of those numbers on the left that were just given to us on the preceding slide, and you have natural log of K2, that's our unknown, over K1, we stated that was 1.35 times 10 to the negative fourth, equals negative activation energy, that's 102,000 joules per mole, over the gas constant, 8.31 joules per mole Kelvin. And then you have T1 and T2. Now be sure you have them matched up properly. The K1 was 308, and the K for reaction 1 was 1.35 times 10 to the minus fourth. So you want to be sure that you have those properly. All right. You basically just crunch all those numbers carefully. Be sure you don't make a mistake. And you have to use your inverse property for logs and natural logs. So raising everything to the e power down, raising e to the power of everything on both sides, you end up with the numbers down below. So just go ahead and study those numbers and be sure you understand how they were derived. So we look over in the blue box on the bottom left. It says K2 is 8.18 times 10 to the negative 7th. This is less than K1, which is 1.35 times 10 to the negative fourth, because the reaction runs slower at 0 degrees centigrade than at 35 degrees centigrade, as we would expect. The last concept we're going to deal with kinetics is called a reaction mechanism. And this is a series of steps that a reaction follows to get from reactants to products. So when you look at the reaction 2NO plus O2 to give you 2NO2, you see it's a balanced reaction, but that doesn't just magically happen. There's a series of steps where the NO has to break apart, where the O2 has to break apart, and then somehow they have to be put back together to create the 2NO2 molecules. And so how does that happen? That's something that chemists study, is what's the actual path or reaction mechanism that takes place to get from the reactants to the products. Sometimes it is done in a single step, but many times it takes 2 or even 3 steps for it to happen. So here's a series of steps that are needed for that reaction to take place. In the first step, you look at the reactants, you have 2 NO molecules and you have 1 O2 molecule. So what happens first is the 2 NO molecules collide to form N2O2. Okay, but that's not the final product of the overall reaction up above. What then happens is that N2O2 molecule that was the product in step 1 becomes the reactant in step 2, and it collides with the O2 molecule, and that produces 2NO2. So both of those reactions are balanced, and you end up, if you look at the if you add those 2 reactions together, you would notice that you would get the overall reaction up above. In other words, the N2 and O2 cancel out. It's on the right-hand side of step 1 of the arrow, and it's on the left side of the arrow in step 2, so they cancel out. The NO and the NO in step 1 combine to form 2NO, and you see that up above in the initial reaction. And the O2 in step 2 on the left side is in the initial reaction. And then the final product of step 2, 2NO2, is also in the initial reaction. So using the same principles we use for adding reactions in Hess's law, you do it here and you find out that those 2 reactions down below, step 1 and step 2, will add up to give you the initial overall reaction. So N2O2 does not appear in the original reaction, but it appears as a product in step 1 and is consumed as a reactant in step 2. This is called an intermediate. So an intermediate appears as a product in the middle of the reaction and disappears before the reaction is over. And each of the individual steps of this reaction mechanism is called an elementary step. Okay, so let's take an example here. Given the reaction H2O2 plus 2H plus 2I, you see there's some ions in there, will give you I2 plus 2H2O. So it's been experimentally determined. Now we're going way back to the beginning of this unit where you had all of that data, the rates and the different concentrations, and you had to hold one constant and see how the other one affected the rate. So that's what they mean has been experimentally determined, that the rate law for the reaction is rate equals K times the concentration of H2O2 times the concentration of I minus. So just a few comments about this. So that's the rate law for this particular reaction. You see that H2O2 is first order, that I minus is first order, and that H plus is 0th order. The reason you know that is because you don't see it in the rate law there, so it has no effect on the rate of the reaction. So that's the overall rate law for that reaction up on the top. Now it's been determined, and again, this is not something you're ever expected to figure out. It's something you would be given, are these steps down below, these elementary steps. So you're being given 3 elementary steps. And what you do is write the rate law for each step. Now this is something you can do, and there's a special rule that applies to elementary steps that we said did not apply to a general reaction like the one up on the top. And let's read that down below. It's in the blue box. For an elementary reaction, you can use the coefficient on the reactants as the exponents in the rate law, just for that particular elementary step. Remember, we learned earlier in this unit that you must determine exponents for the overall reaction experimentally. So for the rate law that you see on the screen there, rate equals K, concentration H2O2, concentration of I, those exponents of 1 above H2O2 and above I, you can't determine those from the coefficients in the chemical reaction. You have to determine those experimentally. But in elementary steps, you can use the coefficients. So let's look at step 1. You have H2O2 has a coefficient of 1 because there's no number there. So that means over on the right where the rate law for step 1 is, H2O2 is raised to the first power. I minus has no coefficient, which means it's 1. So that means the exponent for the I minus concentration over in the rate law for step 1 is also 1. In fact, you'll notice all the coefficients in all these reactions is 1. So for OH minus and H plus, hydroxide and hydronium in step 2 also have coefficients of 1, and therefore the exponents in their rate law for step 2 is also 1. And then finally for HOI and H plus and I minus, the rate, those exponents are going to be 1 as well. And all three of those do show up in the rate law. Okay, so it's been experimentally determined that the rate law for that reaction is what we showed on the previous slide. So the rate mechanism has those 3 elementary steps, same as the previous slide. So you can see that the rate law of the overall reaction is the same as the rate law of step 1. In other words, the rate law for step 1 and the rate law for the overall reaction is K times concentration of H2O2 raised to the first power times concentration of I minus raised to the first power. So be sure you see what's being said there. So the rate law for step 1, the step 1 elementary reaction, is the same as for the overall reaction. This means that step 1 is limiting the speed of the reaction. And therefore, step 1 is called the rate determining step. Think about this. If you have these three elementary reactions running, the overall reaction can only run as fast as the slowest step. The slowest step is going to determine what the speed of the overall reaction is. So therefore, this is a principle you should remember, is that the rate law for the slowest elementary step is going to be the rate law for the overall equation. So convince yourself that the rate law in step 1 and the rate law of the overall reaction up at the top are the same. They look exactly the same. The other two don't. Okay, let's look at some reactions or some examples of reactions that are unimolecular, bimolecular, and intermolecular. Notice as we do this that if you have two of the same reactant, A plus A, that's the same as saying 2A. So if we rewrite the reactions in this format, they appear as follows. So a unimolecular reaction would be A to products. So the rate law for that would be rate equals K, concentration of A. If you have a bimolecular, that would be A plus A. It doesn't have to be, but it could be A plus A, two of the same reactant going to products. So we're going to write that as 2A. Therefore, that coefficient 2 becomes an exponent in the rate law. Again, if it's an elementary step, you can use the coefficient of the reactant as the exponent in the rate law. So rate equals K times the concentration squared. If you have a bimolecular reaction between two different reactants, A plus B to products, then the rate equals K times the concentration of A times concentration of B. If you have a termolecular reaction, all with the same reactant, so it's A plus A plus A, that can be written as 3A, and so the rate equals K, A to the third power. Termolecular with two different reactants, 2A plus B, will give you a law of K, A squared, B. And if it's termolecular with three different reactants, A, B, and C to products, then that would give you rate equals K, concentration A, concentration B, concentration C. So what the point is here, you can see in all 6 of those examples that the exponents in the rate laws do equal the coefficients of the reactants. So as long as these are elementary step reactions, then you can use the coefficients in front of each of the reactants as the exponents in the rate law. And this illustrates that point earlier. So again, let's say it yet again another time. For an elementary reaction only, you can use the coefficient on the reactants as the exponents in the rate laws. Remember, we learned earlier in this unit that you must determine the exponents for the overall reaction experimentally. Okay, so now we're going to look at two examples, and the two examples differ, so we're going to talk about how they differ. And this is to use the elementary steps to produce the overall reaction. So compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So the overall reaction that we're trying to produce here is 2N2O produces 2N2 plus O2. So since the first step is slow, its products N2 and O immediately become reactants for step 2, and the overall reaction is completed. So think about that. The first step is the slower of the two steps. So as soon as step 1 produces its products N2 and O, they're immediately gobbled up by step 2, and the reactants of step 2 are N2O plus O, and they immediately go to products for step 2, and those are and that's going to eventually produce the overall reaction. So step 1 is the slower of the two. As soon as its products are produced, they're immediately going to be used by step 2 to complete the overall reaction. Now convince yourself that that overall reaction, 2N2O produces 2N2 plus O2, is the sum of the two reactions above. And just again, using the same principles we used for Hess's law, just by adding the two elementary reactions. So therefore, the rate law for the overall reaction equals the rate law for the slow step, step 1. And what would that be? Well, there's only one reactant in step 1. It's N2O. It has a coefficient of 1. So the rate law for the overall reaction is going to be rate equals K times the concentration of N2O to the first power. Again, that's the rate law for the first step using just the only reactant that's in step 1, N2O. And there we're adding the reactions, so you can see that the O's cancel out, and you end up with N2O twice on the left side of the arrows, once in step 1, once in step 2. That adds up to 2N2O. And then over on the right side, you have N2 appearing twice on the right side, once in step 1 and once in step 2, so that's 2N2. And then the O2 on the right side of step 2, and that gives you the O2. So that is the overall reaction. Okay, now we're going to look at the different situation. This one's a little more complicated. And this is a rate mechanism for a slow final step. So the second step of the two is the rate determining step. It's the slow step. And that creates just a small complication. So compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction 2NO plus Br2 produces 2NOBr. So let's look at the two reactions. Step 1 is you take two NOs and you combine them to produce N2O2. Now you're seeing something that we've shown a couple of times before, and we really don't get into this concept heavily until the next unit, which is equilibrium. But you see arrows going in both directions, and that's called a reversible reaction, and it means the reaction can either go backwards or forwards. So that's a reversible reaction, and we're making that assumption in this. Many reactions are reversible. They don't just simply go from reactants to products. So in this case, it is a reversible reaction. We're also assuming that step 1 is the fast step, and that it's in equilibrium, meaning it reaches an equilibrium between the left side and the right side. Step 2 is N2O2 plus Br2 produces 2NOBr, and that's going to be the slow step. So again, you want to be sure you understand that you could add step 1 and step 2 to get the overall reaction down there at the bottom, which is the reaction at the very top. So the rate law for the overall reaction equals the rate law for the slow step, step 2. And we'll call this a temporary rate law. So here's what you will see. If you look at this slow step, here's why this what complicates this problem, is that if the step 1 is the fast step, it's going to be producing its product, N2O2, very quickly. But the second step is really slow to pick up that N2O2. The slow guy is slow to grab that N2O2 and put it into the step 2 reaction. So what happens to the N2O2 in a reversible reaction? Some of it goes backwards in step 1, goes back to NO plus NO. So in other words, that N2O2, that's the product of the step 1 reaction, can either jump down into step 2 and become a part of the step 2 reaction, or it can go backwards and go back to the reactants of step 1. So that makes the situation a little more complicated as to what's going to happen to that N2O2. So that's why we call this the temporary rate law, because look at the second step. That's the rate determining step. That means that the rate law for the overall reaction, the one at the very top, should equal the rate law for step 2, since it's the slow step. So what would that rate law be? Well, we see it down at the bottom. The rate would be K times the concentration of N2O2 times the concentration of Br2. In other words, the reactants in step 2 are the reactants that are going to be in the overall rate law. But there's a problem. N2O2 is an intermediate. It shows up at the end of step 1, it enters step 2, and it's not in the final product of the overall reaction. The only thing in the final product of the overall reaction is 2NOBr. So N2O2 is what we defined earlier as being an intermediate. It's created in the middle of the reaction, and it goes away in the middle of the reaction. Well, the problem is you can't have a rate law written in terms of an intermediate. In other words, look at the rate law down at the bottom. K equals N2O2 Br2. You don't have, look up at the original reaction at the very top. You don't have N2O2 anywhere in that original reaction. So how can you have a rate law that has a compound in it that doesn't appear anywhere in the original reaction? You can't. So you have to figure out, how do we substitute that N2O2, substitute something in for it that's in the original reaction. So we're going to find that out on the next slide. So, but there's a problem. The temporary rate law includes an intermediate, N2O2. The final rate law should only include the reactants in the final equation, NO and Br2. For this reason, we need to find a way to express N2O2 in terms of NO and Br, because they are the reactants in the original reaction. So step 1 is NO plus NO gives you N2O2. That's the first elementary step. That's the fast equilibrium reaction. This is a reversible reaction, which means it can go both ways. So it can be written with two different rate laws, one for the forward and one for the reverse reactions. So the forward reaction is going to be just what you see in step 1. It's NO plus NO gives you N2O2. But it can also be written in the other direction with the arrow going backwards. So the reactant would be N2O2 going to NO and NO. So now these are kind of so now you can write the rate law for each of these two reactions, the forward and reverse, as for the forward reaction, rate equals K forward times the concentration of NO squared, because NO is 2NO, that's going to be NO squared. And the reverse reaction is N2O2, and that's going to be rate equals Kr of N2O2. So that's of the reactant of that reaction. Since the rates of the forward and backward in an equilibrium reaction have to be the same, you can set those two rate laws equal to each other. So you have K forward, so you can have K forward of NO squared equals K reverse of N2O2. And we can solve this for N2O2. Sounds like a lot of work, but it gets us to what we're trying to do. So you just do a little algebra and you get N2O2 equals K forward over K reverse over NO squared. And now we can substitute that in. That N2O2 is that intermediate that we cannot have in our final rate law. So when we go to the next slide, and we take that rate law that we had, that temporary rate law that we can't use because it has N2O2 in it, and we substitute in Kf over Kr NO squared, then we basically can combine all of those rate constants, temporary rate constant, and then the forward and reverse rate constants can all combine into the final rate constant for this reaction, so they form the final rate constant K. So the final rate law includes the reactants for the overall reaction, but it does not include intermediates. So rate equals K NO squared Br2. So that's really a load, isn't it? That was a toughie, but I guarantee you it's one of those things, if you practice 3 of them, they become pretty easy. Finally, just a quick mention of catalysts. A catalyst speeds up a chemical reaction without being part of the reaction. A homogeneous catalyst exists in the same phase as reactants, liquid and solid. For a catalyst to work, it must do at least one of the following. 1. Increase the number of collisions of reactant molecules, and 2, lower the activation energy for the reaction, that's EA. So the reaction pathway shows the activation energy, the highest point on the curve, is lowered in the presence of a catalyst. So the beginning and ending energy levels, notice, are not changed. So the catalyst does not change how the reaction begins and how it ends. With or without the catalyst, it's going to begin at a certain energy level and end at a certain energy level. The catalyst just makes it easier to get from the beginning to the ending of the reaction. Okay, so that covers our unit on kinetics. And if you practice these problems a few times, there's no problems in here that are impossible to understand. You just have to practice everything in chemistry, and you will be ready for this. And they will test this pretty regularly, I will say, on the AP exam. So we'll see you in class.